I've told you, practice constantly. We hope to see something very good coming out. You know. Let's hear of you. Your school's name must be heard this year. Yes. Constantly. The chemistry, the physics, for the maths, it's all about practicing.
Sir, please, before you leave us, tell us a little more about counting. So I'm recording.
Oh, okay. Counting is the most fundamental mathematical activity. When you take the basic arithmetic operations that we perform, you realize that what they all boil down to, in essence, is counting. For instance, how do I know that 2 plus 3 is equal to 5? Okay, let's say I have two objects. I must have counted to know that there are two objects over here. Then I also have three objects. This is the addition, the putting together of these two quantities. So I have performed the addition, but how do I know the result of the addition? I have to count. So 1, 2, 3, 4, and 5. So this is how I know that 2 plus 3 is equal to 5. I can express the operation that I have just performed by a gesture. Somebody will do this to show that he is adding 3 to 2. As a math student, I can express the same thing by writing. Let me write. So 2 plus 3. This is a numerical expression of the operation I've just performed. Numerical expression. It is a numerical expression because I have expressed the operation in terms of numerals. These are numerals. Numerals are symbols which we use to represent numbers. We often confuse numerals with numbers. A number is a concept, is an idea. It finds expression in symbols. The symbols are the numerals. So we have a numerical expression. Similarly, multiplication can be reduced to counting. Let's say I want to multiply 2 by 3. So I count 2 and I put it here. I count 2 and I put it here. I count 2 again and I put it here. I have multiplied 2 by 3. If I want to multiply 2 by 4, I'll count another 2. So now I've multiplied 2 by 4. Alright. So I want to know the result of the multiplication of 2 by 3. So I put this together now. And I have to count 1, 2, 3, 4, 5, 6. So I know that 2 times 3 is 6. So you see how the process in essence is counting. Division. Let's say I want to divide 8. I've added 2 more, so I have 8 objects here by 2. As for division, once you are doing it, it presupposes that there is an entity that is receiving. Division is sharing. It may be a human being or any other object or a place, somewhere that the quantity you are dividing must be going to a destination. So let me create some destination over here. So I'm dividing 8 by 2. So these are the two. So to be fair, 1 goes here, 1 goes here, 1 here, 1 here, 1 here, 1 here, 1 here, and 1 here. I have finished the division. Now I want to know the result, what each person will receive. So I count 1, 2, 3, 4. 1, 2, 3, 4. And so I say that 8 divided by 2 is 4. If I have 9 objects, then I would have report the result as 9 divided by 2 is 4 remainder 1. Subtraction, same. Let's say I want to subtract. So I have 6 objects over here now. 1, 2, 3, 4, 5, 6. I want to subtract 4 from 6. I have the 6 I've counted. Counting is always involved, it's fundamental. So if it is 6 minus 4, then I have to take away 4. 1, 2, 3, 4. This is the result of the subtraction, which I have to count to know. So I have 1, I have 2. That is the counting. Let me seize this opportunity you have given me to address the issue of division by 0 once more. You see, like I said already, if you are dividing, then there's a receiver. So if I'm dividing these 6 markers amongst 2 individuals, these are the individuals. 1, 1, 1, 1, 1, 1. So I know that I have 3 here, 3 there. 6 divided by 2 is 3. 0 divided by 2. So again, I have the 2 entities here. They are waiting to receive. But I have no markers again. I have no markers. Look, I have no markers. So I can't share to them. That's fine. But I can tell the result. The result is that each one of these entities has nothing. And so it makes sense when I write 0 over 2. You can capture since you are recording. 0 over 2 is equal to 0. I have nothing. 2 people wanted to receive, and each one of them receives nothing. That's fun. But when you say, let me use this to clean. When you say 2 over 0, here you have no one to receive, so the recipients, they are no longer here. But you have 2 objects, no recipients. How are you going to share this when there is no one to receive? That is why we say that division by 0 is an undefined expression. That is to say that you cannot perform the operation that this expression is representing. You've seen, I still have the 2. I cannot share. The result of the division, as we report, is what becomes of the recipients. When I was dividing 0 by 2, we saw what became of the recipients or the receivers. They had nothing. That is why we wrote 0 over 2 is 0. But in this case, there's no one to receive. So this is undefined. Now, if you say, shouldn't we say this is 0 since nobody has received anything. That means you are treating nothing as if it is something. You are saying nobody has received. No, nothing is not a thing. And that will support the idea that many people have that mathematical expressions are just meaningless symbols that mathematicians use to trouble people. Mathematical expressions generally are abstractions of what we do in everyday life. And so if you are going to give an expression which doesn't correspond to an operation that we perform, we will say it is undefined. In the same vein that 2 over 0 is undefined, 0 over 0 is undefined. Here too, people may say, but haven't we learned that any number divided by itself is 1? No, 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 we haven't learned that. We don't know that. Some people say that. Mathematics doesn't know that. Mathematics knows that this is an undefined expression. In mathematical analysis, 0 over 0 is one of the things we refer to as an indeterminate form. What that means is that 0 over 0 will result if you try to find the limit of a rational function by directly substituting the limiting value or the value that s is approaching into the numerator and the denominator. Let me give you an example. So you want to evaluate limit as s approaches 0 of x over 2x. And then you substitute 0 at the top. You substitute 0 for x here too. That will give you 0 over 0. But this function, if you analyze it very well, as x approaches 0, this function approaches 1/2. How do I get the 1/2? I divide this x by x to get 1 and I'm left with half. So if I'm dividing x by x and I'm saying the result is 1, it means I'm saying x is not equal to 0, because if x is 0, then x over x is not 1. But limit as s approaches 0 is not what happens to the function where x is 0. It's what happens to the function when s gets closer and very close, arbitrarily close to 0. And so I'm justified to remove the case of 0. Anytime you said x over x is 1, you are saying x is not 0. So you have to be careful. If it is possible for x to be 0 and you do that, then you are wrong. As you will do in this case, if you have the equation x squared equals x, and you are looking for the truth set, and you cancel out, you divide, and you say this is 1 and this is s, you end up with s equals 1. This is an incomplete solution. The solution to this equation can be best obtained when you bring the x here, factorize, and you have x minus 1 equals 0. Then you will know that x is equal to 0 or 1. So you need to be careful. Let me go back to what I was saying about 0 over 0 being indeterminate. Now, if you try to evaluate limit as s approaches 0 of the function x over 3x, again, if you substitute 0 here and here directly, you are going to have 0 over 3 times 0, which will give you 0 over 0. But this function x on 3s actually approaches 1/3, 1 over 3, as s approaches 0. So what we are saying when we say that 0 over 0 is an indeterminate form is that you cannot use this expression to determine this limit, because there are many expressions that will lead you to the 0 over 0. And all those expressions don't have the same limit. The x over 2x has the limit 1 half as s approaches 0. The x over 3x has the limit 1/3 as s approaches 0. You can just imagine what will happen. X over 5x will have the limit 1/5 as s approaches 0. So different limits can, in trying to find different limits, you arrive at this. So this alone, this does not determine the limit. That is why it is an indeterminate form. It doesn't mean it is defined. So now let me go back to the counting. We have justified the importance of counting in our subject. It is very fundamental to the subject. I have said that already. But it should be obvious to us that there are certain situations in which we cannot count one by one, as I have said. It will take a long time when we try to do that for us to achieve our aim. So this is the reason why we have to deduce counting formally. Consider a situation where have converted this table into a board by force. Teachers are always doing this. So consider a situation where you want to, let me show you, find the number of integers between something like 45 and 300. You cannot, if you count from 46, that will take you a long time. In this case, to know the number of integers between these two, we take the smaller one from the bigger one, and then we subtract 1 from that. So we have 255 minus 1. That will give us 254. And you may ask, why are we taking -1 again? Isn't it enough that we take the 45 from it? Now, we want to know the number of integers between these two. If you take 45 out from 300, you still have the 300 included. And so this -1 is removing the 300. So in general, to know the number of integers between A and B, where B is greater than A, we use the formula B minus A minus 1. The other one is you want to know the number of integers from, let's say, A to B. In that case, we use the formula B minus A plus 1. So again, why the plus 1? Now, if you perform B minus A, you have removed the A. As in this case, when you do this, the 45 is out. But the greater number is still here, but you have removed the A. But you want from A to B, so A must be passed. So the addition of the 1 is including the A. So if we want to know, for instance, the number of integers from 6 to 10, if we subtract, we are going to get 4. But we can count. If we count, we have 6, 7, 8, 9, 10. How many do we have here? 1, 2, 3, 4, 5. So they are 5. So just doing the subtraction will not give us the right answer. Finally, before I leave you, I spoke about you having large volume of things to count. You may also find yourself in a situation where the counting process is complex. So let's say you have 3 students in a science A class, and then you have, so let those students be, okay, let me call them A, B, C, and then you have I hope you can capture well since you are recording. Um, let's just call them 1, 2, 3, 4. Now you want to select two students from A and B such that one student comes from A and one student comes from B. In how many ways are you going to be able to do this? This is also a counting problem. Now, because it is possible to take a member from this set in three ways, and it is possible to select a member from this set in four ways, you arrive at the fact that the number of ways in which you can pick one from here will be 3 times 4. This is what we call the fundamental principle of counting. This is the simplest form of the expression of the fundamental principle. The fundamental principle generally says that you have activities A1, A2, A3, and so on up to AN to perform. And then activity 1 can be performed in W1 ways, activity 2, W2 ways, and so forth. You can perform the last activity in WN ways. Then, in order to perform activity 1, 2, 3 up to N simultaneously, you have W1 times W2 times W3 times and so forth times WN ways of performing the activities simultaneously. That's a very useful one. This is the case where you want to select, in this example we have given, you want to select one from here. So if, for example, so this is a generalization. If you wanted to select two members from science A and three members from science B, then you have to be asking yourself, in how many ways can I select two from here? In how many ways can I select three from here? You find that you can select two from here in three combination two ways. And you can select three from here in four combination three ways. So this is another thing we have to take time to talk about, probably not today. Now we know the number of ways in which we can perform this activity. We know the number of ways we can perform this activity. The fundamental principle of counting tells us that the number of ways to do that simultaneously is the product of the number of ways. So from a simple process of counting that we do from the basic school, our needs or the situations become more and more complex, but it all begins from one basis. So I think I have addressed briefly to you, haven't I, the
Yes.
issue of counting. It's been a nice time here with you. If God permits and I return here someday, we will have time to vibe more on math. Thank you. I can go now.